So hi everyone and
So let me
welcome to
start.
this seminar. No, it's okay. You can put it on.
Can I?
So today we have Niccolò Zaghi, who is now a postdoctoral fellow in Nordita, in Stockholm, and we done the PhD in Imperial College in London. So today we'll talk about response theory and reaction coordinates and critical phenomena. So more dynamical system seminar today, but later we'll have a great discussion on the PhD. So Nicola, let's start with this part. Thank you for
Okay.
accepting an invitation as well.
No, thank you very much. Thank you very much. It's very nice to be here, and it's 20 minutes, right? More or less.
Yeah, more or less.
Part.
Yes.
More or less.
So that we have time for discussion later. Yes.
Yeah. Can you see my cursor as well, or not?
Yes.
Wow, this is amazing. Okay, cool. I'll start. Yes. No. Thank you very much. I really like to see some people that I knew already. So and maybe they are coming to Stockholm. So that's very nice. So this is a project that I started during my PhD, and I thought it was appropriate as well because we're going to have a discussion about the PhD later. So it's nice to see that things continue with time. So basically, I will talk today about multi-agent systems, about interacting systems. What are these? Why is it important? The way I see it is that these systems, these models, are basically the microscopic kinetic perspective on the collective behavior that basically are featured in so many phenomena in the natural sciences. And basically, multi-agent systems are just elementary components that are interacting with each other, leading to these emergent behaviors. The applications of these models are all over science, as I said, starting from the synchronization of nonlinear oscillators and going to the whole brain dynamics, but also they're used for sociology, opinion dynamics, and all over the place. I really like the application that is kind of recent about the training of neural networks, and I will talk a bit about this later. The models that I will be considering are called weakly interaction diffusions. And I'm trying to find my cursor, I cannot find it now. Wait, can I do this? Okay. To just quickly. Okay. So basically, I cannot find it. I don't know if you can see it, but it's fine.
No,
I can just.
We lost the cursor. Yeah.
Yeah, we lost the cursor. I don't know why.
Now we have. If it's okay, we can.
Oh, this is okay for me, but I don't know if it's okay for you.
Yeah, it's fine. It's fine.
Okay.
We can leave it like this. Perfect.
So basically, the models I'm considering are given according to these stochastic differential equations, where on each node of this network, you have a dynamical system that evolves with its own dynamics given by this vector field F. And this you can think of a very general dynamics. It could be a gradient system, it could be something that is oscillating, or something that maybe is chaotic. And also we are allowing each of these agents to be different. So they're not identical, meaning that we associate to each agent a set of parameter H, and this set of parameter is different from each one of them and is extracted, is drawn from a common distribution mu, which we call the quench disorder distribution. These agents, and this is the important part, are also coupled together via this pairwise interaction kernel K. So the interactions are pairwise, and in general, there could be a network topology, an underlying network topology. In this talk, I will be considering a complete graph, so purely mean field interactions, but there are generalizations, and this is something I'm working on in this research fellowship in Stockholm, in which this network has a graphon structure. We take these interactions to be reciprocal in order for them to satisfy the third Newton's law. So they're basically antisymmetric. And also, we allow the dynamics of each of these agents to be stochastic, so with possibly a state-dependent diffusion matrix. So this is the class of models that we're considering. And why are these models very important? It's because they're used constantly in science to describe phase transitions, meaning change of macroscopic behavior of the system, which we observe strictly when the number of these agents goes to infinity. I wanted to spend some time discussing about these mean field models and why they're important, because they were introduced in a kind of toy models that we could kind of solve, and but now they have applications all over science, and I will show maybe why this is the case. So we can mention the typical case of globally coupled oscillator, and which are models where you study how synchronization happens spontaneously from these oscillators. But also, and this is what I was mentioning before, there are applications regarding neural networks. And in fact, neural networks can be thought of interacting particle systems. And very briefly, the aim of neural networks basically is, if you have a function f that you want, basically you want to approximate, you want to find this function f that we call the target function. And the way you do it is you create an approximation, and the approximation is through this function phi that you choose, and these parameters c and y. The way you find the target function is that you define a loss function, and then you optimize this loss function. You create some kind of dynamics that optimizes this loss function, and the minimum of such will give you somehow the target function, your approximation. And a classical algorithm to do this is the stochastic gradient descent, and this can be interpreted exactly as an interacting particle system. That is, agents that are interacting, where the parameters of the neural networks can be interpreted as the particle, as the agents, and the loss function as the interaction structure among them at the coupling, at the kernel that we saw before. And also, mean field models are routinely used for describing the dynamics of neurons, and they're introduced to link the microdynamics of each neuron, like the dynamics of the membrane potential, to the activity of the whole ensemble. And there are a lot of models doing this. Why are these so important? Why are these models so important? It's because we can actually take the thermodynamic limits of these models, and we can find, let's say, a continuum description of these models that is given by what is called propagation of chaos. And propagation of chaos is, let's say, a mathematical property, meaning that if you take the n particle system and these interacting systems are interacting with each other, you say that propagation of chaos holds when you have asymptotic statistical independence, meaning that the more of these agents you have, the more statistically independent they become. And this is somewhat counterintuitive, but actually, this is not just a mathematical property, it's an interesting phenomenon that happens in science, in nature as well. And I was attending a conference a few days ago, and the speaker gave this very nice example of why propagation of chaos can be expected to hold in nature. And the speaker mentioned this study from Ecker et al. In Science, and basically they looked at the activity of the neurons in the primary visual cortex of monkeys, I think, and they showed basically you would think that these neurons are close to each other and are interacting at the common, and they share common inputs. So you think that they would be very correlated in a statistical sense. But actually, if you look at the correlation, this is this RSC, so what's on the y-axis, you can see that as you vary this, which is basically some kind of degree of correlation, a spatial correlation between the neurons, this correlation stays very close to zero. It's not much. And actually they compared the analysis was more sophisticated, and they compared, they can say basically that the data they have is compatible to having zero correlation or very low correlation. And this is a nice confirmation that propagation of chaos, that's why these models are useful, because they kind of describe what happens in some systems. In a more mathematical way, you say that propagation of chaos happens when you take the n-particle system, associated to this n-particle system, you have a distribution, and the distribution involves all the particles. And propagation of chaos simply states that this distribution, the n-particle distribution, in the limit, in the thermodynamic limit, it factorizes in identical terms, meaning that the particles are independent, where the single mean field particle is described by a single probability distribution rho that satisfies this equation. And this equation is, let's say, a generalization of the Fokker-Planck equation. It's, as I said, an equation for the single particle, the single agent, and it's called McKean-Vlasov equation. And maybe you can see that this part here in the drift and this part here in the drift are what usually happens, what you usually have in a single particle Fokker-Planck equation. But there's also another term, which is what makes everything interesting, where you have a convolution of the interaction K, interaction kernel K, with the probability distribution itself. So this equation is nonlinear and non-local, and that's why it's more complicated to study. But it's still a single particle equation. And also I wanted to mention that if your agents are non-identical, then this quench disorder in the dynamics manifests itself in the thermodynamic limit as this integral over all values of the quench disorder. This framework is suitable, though, to study phase transitions. And in this case, phase transitions are identified as the solution, this exchange of stability of solutions of this equation. So contrary to a normal Fokker-Planck equation, where most of the times you have only one unique stationary solutions, here you might have more. And as you change the parameters of the system, and in this case, I'm thinking of the parameters of the local dynamics, of the interaction, and of the noise, then you might see that these solutions lose stability. A simple example is which we will see later, is the Kuramoto model, where you have the incoherent solution that loses stability and synchronization happens. But in general, how do you detect phase transitions? And this is a problem because usually what you do is you identify an order parameter, which is kind of a smart collective variable that basically summarizes all the information of the n-particle system in very few degrees of freedom. And then you verify that this order parameter undergoes a sudden change as you change these parameters of the system. The problem is it's not easy to find these order parameters. You can cook up whatever you want to cook up, but maybe the variable you end up with is not a very good variable. And this was the question regarding this project. Can we actually define good order parameter or reaction coordinates for these systems we're looking at? And the answer to this question is yes, kind of yes. And this is what I will try to show now. And it requires two ingredients. As I said, the McKean-Vlasov equation, the nonlinear local Fokker-Planck equation, describes completely the thermodynamic limit. But the catch here is that it's complicated because in theory it's infinite dimensional because the drift term, the interaction, depends on the probability distribution itself. So it has infinite degrees of freedom. But the first ingredient that we require is we realize that if you ask this simple condition on the kernel, on the interaction kernel, meaning you ask that the kernel is separable, meaning that this function of two arguments can be written as a decomposition of terms that only depend either on y or on x. Then, and a simple example is like when you have linear forces, for example. Linear forces means just that you have x minus y. And so, of course, you can simply divide this dependence on x and y. And then what was infinite dimensional, we can show that becomes finite dimensional, meaning that the interaction part of the equation, which is this one, can be written in terms of a finite number of this function a that take place in the decomposition of the kernel. And I won't show this how it works, but it's simple once you realize this condition. And so these observables A's that are defined through the microscopic coupling of the system are actually not just random observables of the system, but they actually give a lot of information regarding the dynamics of the whole system, as they carry correlation, memory properties, and also they determine resilience of the system, of the whole system to perturbations. But most importantly, they fully characterize the development of phase transition in the system. And this is where the second ingredient comes into, and which is you need, once you have these variables, you need to study the system through a linear response perspective. And I have, I don't know if you're familiar with linear response, but I have a very simple slide describing what it is. And basically, it's, let's say, an old theory, but still very valid in these days. And basically, the goal of response theory is to predict the change of statistical properties of general systems after you apply some perturbations, external perturbations. And in a way, this relates forced and unforced variability of the system. A classic example is for example, the climate crisis, where you want to identify what the response of some observables of the climate change as for example, you increase the CO2 concentration. And actually, that problem can be studied through response theory. In a mathematical way, it means that if you have a system which is described by a probability distribution mu naught, which is the unperturbed measure, and you take an observables and you assume that that you have an ergodic measure, meaning that if you take the time average of the observables of an observable during some evolution of time, then this is going to be the same as the phase space average with this measure mu naught. Then you think of, this is the unperturbed system. And then you think of applying some kind of perturbation, meaning that the measure will change somehow. And I denote this perturbation with this epsilon, and you can think of some parameter. A linear response theory, the goal is to find a perturbative expansion in this parameter, and you say that the new average of the observables is the unperturbed one plus something that is linear with epsilon. And this something, of course, is just the derivative of this with respect to epsilon. And the whole goal of response theory is to find what that derivative is. And this has been, let's say, found for stochastic differential equations. And the idea, if you have a stochastic differential equation, this sort, deterministic plus stochastic, and then you perturb the drift, and this drift, this perturbation is proportional to epsilon, which is small, but it could be literally very, very generic. It could be state dependent, it could be time dependent. Then the response theory says that the perturbation of any observable is given by a convolution of the time dependent perturbation and the Green's function of the system. And the Green's function is a complicated object that encodes all positive and negative feedbacks. but depends only on the properties of the unperturbed system. So from the unperturbed system, you can extract information of how this will react to perturbation. And of course, it depends on the specifics of the perturbation. So it depends on the pattern X. So the idea is we wanted to study how this, going back to our system, we wanted to study how the thermodynamic limit of our system reacted to some kind of perturbations. So we did the whole linear response machinery. And what I want you to look at is this equation. And this equation says that if you observe how these reaction coordinates that we defined some slides before react to some kind of perturbations, then the responses can be written in two terms. And this is different from the linear response theory that I showed you before for finite dimensional system. And it has two contributions. And the first contribution is this one, and it can be interpreted as the response of a single mean field agent plus, and this is mediated through a Green's function, a single agent Green's function, plus something that depends on the coupling. And this, as you can see here, this something more, this contribution comes from a memory effect generated by all the other reaction coordinates. So basically the reaction coordinate I depends on all the other variables J. But the nice thing is that this description is coherent. So you just need those reaction coordinates. You don't need anything else. And actually it's easier to disentangle these two effects of the response if you look at frequency space. And in frequency space, so you're looking at the response of the observables at frequency omega, then you can write it just by taking a Fourier transform of the previous equation as in this way. And you're saying that the response of frequency omega is just, is the perturbation, the time-dependent perturbation at frequency omega, modulated by what is called the susceptibility of the system. And the susceptibility of the system can be written in two terms. Well, not in two terms, in a factorization of two terms. One is the susceptibility of the single agent, but these susceptibilities renormalized somehow by this matrix P that describe all the feedback and coupling among the agents. And this, if you're familiar with linear system with feedback, is exactly like this. It's basically apply an input perturbation, and what you have in the output is not just modulated by the single agent susceptibility, but there is a feedback as well, given by the coupling and mediated by all the other reaction coordinates. And what I wanted to say here is that these equations describe the full response of the system. And there are two interesting regimes of the response. And it could be the smooth regime. So you're saying how things change as you perturb the system, and you expect that your observables change smoothly. And this mathematically means that this function, the susceptibility, is an analytic function, and it has nice mathematical properties. But there is also a critical regime of the response. And the critical regime is that when you apply perturbation and the system responds wildly, meaning that you have a divergence of these response properties. And mathematically, this means that the susceptibility develops some singularities for some critical frequencies omega. And from this equation, you can see that this criticality in the response either comes from the single agent susceptibility, meaning that you perturb the system and every single agent explodes, or from the matrix P. And if the singularity comes from the matrix P, we identify this as a phase transition, as the usual scenario of phase transitions, where each agent is well behaved, but the interactions among them make the whole system explode. And the take-home message from this slide is that if you have a phase transition, you expect that the susceptibility can be written as, in the simplest case, as having a simple pole, a simple singularity at a critical frequency omega star. And we identify two scenarios when this omega star is 0, meaning that you perturb the system and the system explodes, but it has no oscillations, or when you have two symmetric poles, meaning that you have some oscillations in the system. And if you just an example of this, you can use this framework to study, to rephrase, if you want, the onset of synchronization of the Kuramoto model. And maybe you're familiar with the Kuramoto model. You have some oscillators. Each one of them has its own intrinsic frequency, h, and then you have a coupling among them, which is sinusoidal. And it is simple to see that the incoherent state, as I said at the beginning, meaning the uniform state, is a solution of the Kuramoto model, meaning that all the oscillators, they are incoherently, they oscillate incoherently. The Kuramoto is a class of models that can be studied in this framework because it has a separate kernel. And what I wanted to show you is that the recipe of saying that if you look at values in which this matrix is invertible, you find phase transitions. We apply this to the Kuramoto model, and this is what you observe. We know that the Kuramoto model has some phase transitions. This is known in the literature, and it has different ways of how this incoherent state can lose its stability. And if you do this calculation, and you can show that you have a static phase transition, meaning that this pole is in 0, and you can actually find the critical value of the parameter. But the important thing here is that we did some numerical simulations, and you can evaluate the Green's function, and you can evaluate the susceptibility of the total system. And what you observe is that you actually have this singular behavior that you see here. And in black lines, you see the response, the susceptibility of a non-critical setting. And as you can see, of course, you have some noise, but it has a very smooth behavior. However, in critical settings, when you have this phase transition, you see that the susceptibility develops a critical behavior, a diverging behavior. And actually, this diverging behavior depends on n, meaning that, of course, here we're in finite systems, so there is some finite size effect, and this finite size effect can be parameterized in this way, saying that the susceptibility doesn't have a singularity in omega star, but this singularity is modified, meaning that it has been shifted slightly in away from this omega star, and this gamma n vanishes in the thermodynamic limit, and one recovers the susceptibility. And we also studied dynamical phase transitions, and what you see is that you still find this, let's say, universal structure of the susceptibility. In this case, of course, you have this resonance at a non-vanishing frequency. But I also wanted to say that this framework is useful for understanding other physical phenomena. For example, the properties of the phase transitions are related to this constant k here, which is the residue of the singularity. And the residue is related to how the system responds to some driving forces, meaning we know that this system will react wildly, the oscillations will be highly resonant with the forcing, but will the system adiabatically follow the forcing? This is given by the residue. And for example, if you think of driving the system with a sinusoidal forcing omega, then you can see that the response, this is very easy, it has a in-phase component, but it also has an out-of-phase, completely in quadrature component, given by the real part of the residue. And here are some simulations, and in the dashed line is the forcing, and as you can see, the response is shifted, and the shift is actually this. It can be evaluated quantitatively, and it's related to the ratio of this real and imaginary part of the component. we also tested this, and this is the last thing I want to say, we also tested this framework in other systems. So you have here like a double well, potential, and interaction towards the mean. And this is a system that has an order, disorder, some kind of easing, continuous limit of the easing model. And you see the exact same thing of the susceptibility developing this singular behavior. And also we tested on other models of synchronization of nonlinear oscillators, and we obtained this. And the hope is to apply this framework to more complicated settings. And as I said, I would like to apply it to graphene structure, to networks with a graphene structure. And this is kind of a research area that, at least in the applied mathematical community, is quite strong at the moment. And I don't know how I'm doing with time, but this is it. I don't have any more slides. Just wanted to give an overview.
Perfect, thank you. Thank you very much, very interesting. So I don't know if we have any questions. Yeah, with time, we don't have a lot of time. Maybe we can have like one question if someone has, and then maybe move on to the other part. I don't know if Lisa.
Can I make a very quick question? Why it's called propagation of chaos, the things at the beginning?
So this is a thing of where is it? It's stuck from a terminology of the 60s, 70s, and basically it is related to molecular chaos, meaning that you have this. If you initialize the system with statistically independent particles, and then you have a dynamics, and you let the dynamics evolve. If propagation of chaos means that you keep having this statistically independence. So this molecular chaos. It just means statistically independence. Independence, okay. Yes.
No, I was just curious for the name, because I mean, I cannot relate the name with the effect.
It's
not chaos in the sense, in the mathematical sense.
No, but if you think it is not. It could be chaotic oscillators that exhibit propagation of chaos, but this is molecular chaos. It's not chaotic dynamics.
When you can separate the probability distribution of the
exactly,
and you don't have the problem of the hierarchy. Okay.
Exactly. But these models, because you can think of propagation of chaos as being the central limit theorem. I'm sorry, the law of large number. But of course, what is interesting is to study fluctuations from this. So people have developed large deviation formalisms to study these problems. So how much the system is away from this factorization.
Okay, nice. Thanks.
I have a question also related to this propagation of chaos. So here it says that basically you can factorize the probability distribution of the status of the system. But afterwards, a bit lost in the derivation. But in the end, in the example, for example, for synchronization, when the system is synchronized, if this propagation of chaos still holds, because these variables are strongly correlated, right, in the synchronized phase.
So the propagation of chaos doesn't. So whenever you, for example, for the Kuramoto model, whenever you write the continuous equation, which is the thermodynamic limit equation, what is usually in the physics community is called the continuous formalism for the Kuramoto model. That is the propagation of chaos, basically, because you're saying that all the oscillators behave the same, but you just have a mean field, which is self-consistently obtained. Of course, the propagation of chaos doesn't hold at the phase transition exactly, because you have, in that case, the strongly correlated. But the way, if you do response, this way of using response theory is the way to study how propagation of chaos doesn't hold. because of course, you know that at the phase
okay.
transition, macroscopic observables, they develop the critical slowing down, right?
Yes.
If you look at the correlation at the phase transition, there is a different scaling with n, and actually this diverges with n. The thing is, this doesn't happen in situations away from the phase transition, and actually this, as you can see from here, like the Green's function, it develops a time scale that depends on n, and this is exactly a different way of observing critical slowing down. But this you can study with the propagation of chaos. Sorry, with the McKean-Vlasov equation, with the propagation of chaos. And it is not a mathematical proof, but it's more like a physical way of why I see this working, is that by doing linear response, by imposing a perturbation that is coherent on all the particles, basically you are kind of projecting the n particle system to the response of the system with the propagation of chaos. This is I'm actually working on the connection between the n particle system and what we observe here, and I think that the time scale that you observe here is exactly the time scale that you observe in a critical slowing down situation. But these problems are not super well studied. There are very few results that study how fluctuations away from the propagation of chaos behave at the phase transition.
Okay.
But you can see I have synchronization and have that propagation of chaos.
Okay. Okay. All right. Thank you.
So I also had other questions, but for now, let's move on to the other part because time is finishing.
Okay. Sorry.
No, it's fine. It was very interesting, maybe different from other seminars, so it was great to have you. So maybe I don't know if you have any other slides, but if you don't.
So
perfect.
I have other slides, but so
Great.
This is about what I had in my personal experience, but I would also like to know about the others. So maybe
Yes.
I will go very super quick through this in 1 minute, and then I have some questions that I very egotistically I decided to choose because I wanted to know your opinion on about these things. So I can tell you just a bit about my experience. I did my master in Italy, and I was part of this super nice research group with which I would interact, at least with a subset of people on a daily basis, and I found that amazing. Then I moved to the UK. I was part of a CDT, which is kind of a PhD program where a bunch of PhD work together, meaning we have separate projects, but you gather together every now and then. And I really like that because you have a sense of belonging to the group. And also I want to say that I really had 2 great supervisors. Like I'm still friends with them, and they're amazing on a both personal and professional level. So this is why maybe I'm a bit worried about why I felt the challenges that I felt during the PhD, because the problem was that neither of these supervisors had a research group. Then COVID happened, and then the 2 supervisors, being professors, they had a very incredibly busy admin and teaching life. So I ended up not having not many interactions with them, and this led to some stagnation when I was having technical problems, or maybe I was having dead ends. I didn't know where to go, and of course you gain independence from this, but also you get a lot of doubts, anxiety. You don't know where you're going to end up in long term in your career, and maybe you spend too much time on a topic and you get bored of it. So these are the main challenges I faced. So my question was, my 2 supervisors are great, but I still had these challenges. Is it because the PhDs are not really structured in the most efficient way? And what would you think the ideal situation would be? And these are some questions that I have in my mind. And the first one is, I really think that it really takes a village to raise a PhD student. Like, you need to have people around. I don't know how the situation is in your case.
I guess also we started this also because of this, like Netflix
Exactly.
started as an answer to this question, maybe. I don't know. But also, what are the other questions? Maybe we can have all of them and then
Oh
we
yeah,
can
no.
randomly.
Well, I also was wondering what the role of a mentor supervisor is. They're of course super busy people, and maybe they didn't have training on how to deal with a PhD student. And so I was wondering, how can you make the most out of it? How can you establish with them a connection that works for you and for them? And the third point is like, how can you be independent but also feel supported? This is still a struggle. I'm doing a research fellowship, which you're totally independent, and I really like this. But maybe because I had this PhD, now I'm used to it. So, but if I didn't, I don't know. If I hadn't, I don't know. And then also about the long term of your career. Has your PhD given any experience and teaching on this? I don't know. I think during my PhD, I was discovering things day by day, basically. Then you figure it out, maybe, or maybe you get bored of it. But no one has ever told me, look, this is how it works. This is whom you should talk, or so maybe I was saying this. Maybe it's a structural thing that is wrong. But at least in Italy, the two oldest institutions that haven't changed, and this was actually one of my supervisors telling me this, are the church and the universities. So I guess we have lots of things to change if we want to change it.
Yes, this was something that has come up also in other ways, in other seminars or some personal conversations, for example, in last conference, that we talked about exactly this, that most of the things that we learn, we just learn by ourselves. There's no one teaching us, like how do you interact, how do you start a collaboration, how do you choose if you have to do this project or the other project. Mostly depends on your supervisor, but most of the times, even with good supervisors, as you said, you don't even get that. So yeah, it's an open question. Let's see, there is Silvia writing something in the chat. Maybe I'll read it to you. So during pandemic, my supervisor used to organize this week meeting, one each 2 days. Okay, so that was really good for the speed. So yes, I think that the presence of research group is useful, but I'm biased by my good experience, of course. Maybe in different situations could be stressful because of the social pressure you can feel in that case.
Okay, yes, no, I see that. Like, I really feel like a research, at least for me, I don't get social anxiety. I like to interact with people, but I also know that, as you said, establishing collaborations is incredibly hard. It actually, like, for example, you go to conferences, as we were discussing before, you have lots of chats, but if you don't have persistence in these chats, then it doesn't really lead to a collaboration. So maybe if you have a research group and it's like people that you meet regularly, then yes, of course, it's way easier.
Yeah. Also, sometimes you have the opposite problem. Like you go to a conference, you start different chats, and maybe you have so many cool ideas and projects, and then
you're stuck. Yeah.
How do you do that?
You're overwhelmed. Yeah. I will, at least in my experience, was I really learned that if you want something, you kind of need to be clear about it. And once you have your clear mind, then if you ask to your supervisor directly, then probably they would give you, at least in my experience, a very good idea. But sometimes it really takes time to figure out what you want or what's happening to you and what's happening in your PhD as well. So it's in that in between, before you actually realize what you need and what you want, that I really think a more structured support network would happen, would take place.
From the
I don't know if the yes.
I
So
think
there
Sorry,
is,
I was
again,
reading Silvia's.
I think a good way to practice independence from your group supervisor is to go to conferences without them. It helps you to face what is preparing a talk, giving a talk, making new connections outside your comfort zone.
Yeah, that's very true. That's very true. But I personally don't super enjoy very big dry conferences, meaning that you give your talk and then it's kind of a self-indulgent thing, if you want. You've given the talk, it went well, it went bad, but it didn't have a connection to the audience or to some people, because that's not the settings that maybe is suitable for these things. Like, I really enjoy way more when you have a dialogue, scientific dialogue. And you can say wrong things, you can say good things, and it's ups and downs. And it's not like one being on stage and giving the full picture.
Well, that's why I think that in the conference, especially the bigger ones, you just go there to kind of like go for an update about what's happening in research around you. And then the real socialize and creating collaboration, exchange of ideas, like, but for you, like, that you can benefit from, like, to start collaborations or whatever, is when you talk to the people, like, you're doing something nice, or maybe you're just having a beer and say, okay, so like, what do you talk? And then you start, and I guess, but that's something that probably requires to have a bit of like, you have to be a social person, you know, like you have to go to a person and say, how to, like, you don't know the person, like, oh, hi, blah blah blah, and start a conversation randomly, because otherwise that's the skill that you need to have probably as a researcher. You need to be a social person, otherwise it's complicated, I guess.
Totally agree. I just say maybe this could be implemented in a more structured way. I mean, like, for example, this initiative is great for these types of dialogues as well. But it really, like, usually these initiatives are bottom up, meaning that it's some students very motivated that decide, oh yeah, we're gonna do this. It would be nice to have something that meets in between a bottom up and a top down approach. In some sort of way.
Yeah, I guess that's why, as I was saying before, we are doing this kind of, like, it's not a normal seminar. There is a part where we discuss of a problem, and maybe one of these discussions will lead to a big change, maybe in the way some things are done. So there is Silvia again about the last question about the long term. Somehow my PhD gives me the tools, in the sense that I'm not now into the game, so I know the rules, I have experience and connections, but still not clear in my mind what does it mean to continue in academia in terms of how a postdoc differs from a PhD. Is it the same? Is differences? How? Whatever. I don't know what you think, Enrico.
Well, now I'm doing a research fellowship, meaning that you don't have a supervisor at all. So you like you said postdoc, and you have a supervisor. So you might end up being very constricted in that sense. But no, like, in a research fellowship, to me, it's very exciting because it's independent. You can talk to people. It's also you, in that case, you really don't have a support network with you. I mean, of course, my supervisors are, as I said, but just because I had amazing supervisors, and I'm still in touch with them, even in a mentorship situation. Like, if I am in doubt regarding something, I would ask them, because their opinion, it doesn't mean that I will follow it or that it's going to be clarifying. but at least it's another opinion. And they have been, as you said, they have been in the game for way longer, so they kind of know it as well. Also in, and this I didn't write, but also in the grant proposal writing situation that every academic needs to face at one point. They know
Yeah,
what
for example,
works.
for that, let's take that example. Like when you, for grant proposals, we don't have any kind of training at all. Like
Nothing.
zero.
Nothing. Yes. It's true. It's true. And I have been writing a few, and there are very simple things that you wouldn't think of, but that's how the people, the committees, the institutions evaluating the grants, they actually look at those things. And very naively, you wouldn't put them, or you would think, okay, they know this. I mean, they know that you've received. I mean, I'm giving you the CV, so they know what I've done, what prizes, awards I've won, or other people have won. But no, the repetition. I found that repetition is incredibly useful there.
So in this sense, what we are doing as an initiative, so we're doing 2 panel discussions at NetSci that are exactly towards this kind of problems. Like in the first one, you say like, what is a good paper? What are the features of a good paper or a research plan? What are the editors looking at? What are the examiners of the grant proposals really looking at? So from the point of view of the, so that all the PhD students, or like for example in the second one, the relation with the supervisor, some ways to deal with mental issues in academia. There are things that I think that we need to work on as a community, and provide some more structured ways.
Yeah, like, sorry to cut you off, but in Ordita, I'm part of I'm the chair of the EDI committee, so equality, diversity, inclusivity, depending on the country. And I mean, it's nice. It's very nice to be part of it and to do all these initiatives. But I also see that, of course, you can implement structural change. The thing is, it's very difficult to implement it when you are the one that doesn't have power, meaning that and if for an academic in our stage of career, that means that you don't have financial stability, you don't have time, like you have a limited time. So how can you carry on a bigger project when you know that you're going to move place? Of course you can, and we're all doing it. But I would really like to see more awareness from the higher levels about these issues.
I had a discussion recently about this kind of problems. I mean, whatever the problem, let's say, for example, journals or any other problem that we have as researchers. And yeah, I guess nobody in the higher hierarchies will have any like actually do something. And on the other hand, we don't have the stability to do it. But that's the problem of any society, like in society, the worker works, no? So you have the people that like the poor people that have problems, maybe, I don't know, and so they raise issues, and then at some point, if that's unbearable for them, they start to do something together. So I think that's the only way you can actually have this cultural, like in climate change, like the politics didn't even care, and then many attempts, but not just by one person, because it's gonna be destroyed, that person, but by the whole community. So if all PhD students say, okay, the way supervision is not done well, it's not good, then it's gonna be changed. But maybe you start small, and then but I think that's the only way. You just need to be more focused on what you actually want to change,
Yes,
but I think that's the only way.
I think in this, I have 2 opinions, at least. One is that you're fighting against academic environments, which have a lot of problems. regarding EDI and regarding wellness, regarding bullying, regarding harassment, which, for example, in industry, you might not have. I mean, it's way more clear the way people should behave than maybe in academia it does. And also,
and why do you
you're
think
fighting.
so?
I honestly just inertia, basically inertia. The universities are much bigger environments. Maybe on a systemic way, you don't have that sensitivity. So the universities haven't changed yet, and also you have that. What is it called? The analogy, for example, for EDI, you have the analogy of the leaky pipe. In your academic career, you start in undergrad, you have lots of diversity, and then everything gets filtered out because all the diversity goes away. And of course, then you have a self-reinforcing. At the end, you're going to have a self-reinforcing environment because you don't have much representation. You don't have in the same room. You don't have the people that maybe can like. You don't have that diversity that can lead to that change, because those problems will be overlooked or it will take more time. Yeah, this is getting very dark now. No, but
what was your second opinion on this? You said you had two.
Yeah, that's a problem with me. I say I have two, and then I remember one.
Okay, sorry.
No. It's what was it? No. Another thing could be that the life of a young academic researcher, that you get scattered around. And I feel like having geographical stability helps with that, because you have a group of people that coherently fight for it. While if you don't, even on a coffee break, if you're scattered around and everyone is so busy, I don't know if this is your experience, but everyone is so busy in academia. Doing what? I'm not sure, but very busy, everyone, from any level of career.
Lisa?
Well, I have two comments, but they are not so related on these topics. One is about the first question, that is my doubt, like our PhD is structured in the more efficient way. Okay, what do you mean with more efficient? Because there is a lot of diversity in each group, with the interaction with your supervisor, the character, like the behavior of yourself and the behavior of the supervisor can be very different. So it would be difficult to talk about efficiency, no?
Yeah, it's an ill-posed question, of course. I would say like what you said is, to me, is already something. I mean, you're assuming that there is a structure, that there is a group, that there is situations where these conversations happen, but this is highly dependent on whom you end up with, right? I guess that's everywhere, that is true, but at least but because I think nothing is structured, not even at the supervising level. I mean, I think the supervisors are kind of figuring out how to supervise as well. Or they do have training. I ask my supervisors whether they have training, and they have kind of management training, but it's more about like, if you become head of department and stuff like this. But they're really supervise, like they're really figuring out as well.
The second comment is is
no.
Do you want to go on?
No.
I don't know if I stop. The second comment was related, but yeah, I mean, I don't know about you guys, but when I was doing my master, nobody told me what a PhD is. Okay, and I'm I'm not saying in the specific sense of, okay, in the first year you will do this, in the second year you, I mean, in general, in a general view of the PhD. Nobody mentioned the PhD. Indeed, I also applied later because I didn't even was aware of doing these things. So, I mean, it could be a first step to try to explain to master students what really a PhD is about, like doing research and learning how to do research. No, I mean, at least in Italy, because I had my experience in Italy, I do my master in Italy, and I didn't have any, neither a small talk about what a PhD is. So it would be beneficial, I guess. A first step to be more efficient at the beginning.
Yes, I missed this as well. But also, I think it really depends on the country as well. Like, I think a PhD in Italy is very different from a PhD in the UK. At least in the UK, my experience was at the beginning, of course, you have a proposal, you have an idea, but of course, you're coming from a master. You don't have the experience of someone that has been in the field for ages. And in the UK, at least to me, it was very much like, so what do you want to work on? What is your project? Which is great, but I would also like some input. But this was, to me, at least in my experience, was the master by research part of, I had this weird situation. You have a master by research plus PhD. And in this master by research, you have this trying to figuring out what you want to do. But no one really gives you much guidance. And so I was coming exactly from my master, where in Italy, I had a kind of an idea that a PhD was, you would work with a supervisor that has an idea, but then of course the direction goes more towards what you want to do, but still you have a macro supervision of the supervisor. In the UK was more the other way. So what do you want to do? Do it, and then let's see if it works, which it's a shot in the dark, at least.
Yeah, it's risky. No.
It's very risky. I don't know, have you had like outreach events? At least in the UK, we had some opportunities in our PhD to go talk to schools, to discuss what the PhD is. But also on our side, I can tell that all the people in my PhD program, they were kind of holding back because they were like, oh, we don't want to scare these people away. Everyone was stressed. I think it was the last year where they were writing the thesis. So they were like, don't do a PhD, it's horrible. So even these outreach events didn't really work maybe the way we wanted it to work.
Yeah, and then there is also the problem that you don't have the time to do it.
Yeah. So maybe we are already experiencing the academic life by not having the time to do things. Like this, I think that this is the definition of professor, no?
Yes. Yeah.
So, Nico, in your idea, what is the role of the mentor or supervisor? How does it develop during the PhD? This role.
That is.
Since you have two also great ones.
That it is. I don't know. I think. You know, I've had some experiences of supervising. Of course, it's not a PhD student, so it's way smaller, and probably I think in my early experiences I would think, oh well, probably I'm over supervising, meaning that you don't allow any kind of independence of the student. Or I mean, there is some independence, of course, but it's, you know, it's a nice feeling when you figure something out and you know that your supervisor has helped you, but you did most of the work, and it's satisfying. But I don't know, it's just a strive to seek this, trying to seek this balance in between macro supervision, meaning, oh, I know you like this, but look, there's a lot of people working on this, or there's a lot of people that are not interested in this. I know it's very interesting to you, but keep this as a side project. Like in my experience, I would really enjoy that. I would have really enjoyed that. You know, like these are the what can happen if you do. I'm not forcing you to do this or this other thing. And again, I think my experience is a bit different in a way because I was part of this PhD program. So basically, I was self-funded and I chose a supervisor. So the supervisor wasn't paying for me. And so maybe their idea wasn't as strongly put in my project, meaning that they didn't force me to do anything. They had a vision. And when I was feeling lost, I went to them and I said, is this good worth of exploring? And sometimes they said, it is interesting, but maybe not worth of exploring. Like, I mean, you can do it, but as you said, you don't have much time. So maybe try to do the other things. And I feel like this would be like regular meetings where you have this. Even if you don't have much, at least in my PhD, I had meetings when I had progress and substantial progress. It wasn't random meetings, random in a wide sense, but I've heard of people having weekly meetings and that worked amazing for them. Even if they didn't have much progress, they could discuss at least some papers that they read together. And that could lead to other ideas, or that could lead to, you know, a more constant supervision. So I feel like having constant meetings is nice. I don't know about you, but did you have this?
I never had constant, never.
Yeah,
Never
same.
schedule. Zero.
I mean, it was not constant for me. It is not constant for me. But when
What?
when I want to discuss something, can you hear me?
Yeah,
Yes.
yes.
Just when I want to discuss something, I go talk to my supervisor, even if I don't have progress, because I spend some times, like long time, not having progress on a problem. So we need idea to try, and I needed to go talk with my supervisor, even if I didn't have any progress at all. It's useful, actually. I mean, even if you don't have nothing to show, but something to talk about, I found it very useful, yes.
So that could be a simple rule to implement, you know.
I do
How to
have
supervise. Oops,
almost
sorry.
a weekly. Sorry.
There is a bit of lag, I guess. So go on, Aline. Go on.
Okay,
Then
so what
Nicola
I'm
will
saying
wrap up.
is basically I had the weekly meeting from the very beginning of my PhD, and indeed it's like I don't know, maybe every week I update what results I've got, and my supervisor may give some feedback saying, okay, maybe this one is interesting, this one we could explore a little bit more, or she has some suggestions on this exploration. And during the whole week, I may find something new from the direction she has mentioned, or find something else where it comes from somewhere else. And yeah, for me, I think this type of supervision indeed helps in terms of making progress in the project. But it seems you will lose some say chances, or some, because you are mainly targeting your project, and actually I think sometimes idea or these new projects come from the other side, not, you know, the exact thing you're focusing on. So maybe I think it's pros and cons. If you have constant meeting on your project, I mean, this is going to happen, right? You discuss mainly on this project, on this specific problem, and yeah, you're very focused. you're making fast progress. But for me, I think I may not have that many new ideas to explore, because I think most of the time I was very focusing on very specific problems. And as for the support from the research group, I definitely agree that a group would be very helpful, because that is what I don't have. We don't have really a research group, although my supervisor have 3 students, and we work on very different subjects, and we literally never have a group meeting. We only met once last summer, or last summer, just some random chat, but not really a proper group meeting. So I sometimes feel lost, but so here's the case. Usually I should, or I'm supposed to discuss these questions with my peers, or the group members, and we maybe figure out something. And for me, because we don't have this kind of environment, what I do is mostly go directly to my supervisor and ask her, okay, if there's something we can try, or if we have this problem. And so this is how discussion goes. It's me directly with the supervisor. And the problem with this type is you can maybe discuss some macroscopic ideas or directions or result to show. But for this microscopic, for example, if I have problem with my code, I literally have no one to discuss with. And this is quite stressful. I mean, I think there's literally no one, because other people do not work on the same project, and clearly you can't really let them to understand your very detailed problem and whatever. And my supervisor even don't use this programming language, so I mean not get very direct help from her. So for this technical issue, I think I have to mainly rely on myself, and sometimes this is quite depressing. Yeah, so I guess the group interaction will definitely help this type of problem in some sense. That is definitely could be optimized.
I was reading some comments on the chat saying that it is true. It's basically you kind of need to work on a microscopic level by yourself, right? If I get correctly the chat. But like I feel like at least in the research group I was having in Italy, it is true that your microscopic problem is yours and just yours. But then there is someone, I mean, we kind of work on similar topics. There is someone that must have had that is an adjacent, at least, problem. And for example, in Ordita, I know of people that one person was doing quantum mechanics, and other person was doing nonequilibrium stat mech, something like this. Then they were talking, and oh, that equation looks very similar. And one person couldn't solve it. The other person was like, oh yeah, no, but actually you can use this technique. They ended up having a paper together. So, I mean, even this being stuck on a microscopic level, then it might lead to something if you have someone to interact to. But yes, you need to have some interaction.
Yeah, I think it's really, really important. I don't know. I often have like very bigger than normal probably size of groups for projects. Like it's not just me in a paper and my supervisor. I actually have no paper with just me and my supervisor, or just me. And I guess that helps. And when in the other cases where it was like just me and then a bunch of professors, maybe so they're not really, it's me just doing the work. it helped a lot just to talk maybe on a break on something with people, anyone, because usually the people you talk to might have an idea of what you're maybe emotionally that they've been through that situation, or sometimes, as Nico said, you might have the same problem or similar, so they can actually help. Even just to say the problem to someone else usually helps. So in that sense, I think, yeah, it's important to have this kind of interactions. Maybe not necessarily a research group, but just someone that is just there that you can talk to, I suppose. Yeah.
Yeah, for sure it helps the spirit.
Yeah.
Yes.
So yeah, I guess we should stop this seminar. I don't know if Nicola, you want to say something else, or if you got some good answers for your questions.
No, I'm very, no, one, I'm super happy about, like, I think these conversations are needed, just having the conversation, because then you know that you're not alone, the struggles of your PhD, a lot of different people have faced them, and yeah, no, so I'm super happy, and happy to continue having them.
Great. So yeah, usually we have like these meetings every 2 weeks, and we are still, as I was saying before, still trying to improve the format. So I don't know if you actually have any feedback on how we could improve, also to reach more early researchers, that could be interested in this. I don't know, what are your ideas on the spot?
On the spot, I don't know. I kind of need to think about it. But I mean, how do the people that participate? How did they get in touch with you? Is it a word of mouth situation, or is it, for example, I knew you, I know Francesco.
So the way it started was by mouth. So basically, like all of our friends and maybe all the professors we had any type of interaction with, like we really just sent emails a lot. And so we gathered quite a number of people, PhD students, that were interested. But then, yes, it's mostly by mouth, more or less. We have a mailing list. There's like more than 100 people, so we always send the emails. Yeah, and Twitter.
Have you looked
helps.
at least for the UK, because I mean, this could be bigger than national, right? It's an international.
Yeah, it's international, yes.
But in the UK, at least, there are these CDTs, the Center for Doctoral Training, and there are a lot of them regarding networks as well. Like my colleague Anodita, she was part of a CDT in Cambridge, I think. No, maybe it's Oxford. I always get confused. But maybe even just talking to the CDT, they have a bigger structure. So it's easier to contact like a reference person, and that reference person can spread the word to the whole network. And that could be, like, you don't need to go to the single professor and then say, oh, we exist, blah, blah, blah.
Yeah.
You can just go to, like, we had an admin person, and she would forward the email to everyone. And I think everyone could benefit from this. So students will come.
Yeah. I guess it's a bit specialized what we do, because we also do the research part, which is mostly in complexity science. And so we also have that part that maybe, like, because I guess in the second part of the seminar, everyone could be interested, It's not you can do theoretical physics or applied physics or mathematics or biochemistry, whatever, it doesn't matter. But for the first part, maybe it's focused only for a specific set of people. So I don't know if that would, yeah.
So I know, at Nordita, we have a similar event where it's called Young Scientific kind of afternoon tea.
Okay.
And basically there is, this is in person, but there is a talk.
Yeah.
But this talk usually tries to cater like a wider audience. So it's an introductory talk on something or a topic. And you don't really need to be, like everyone participates to this.
Okay.
And then after there is this, this is sponsored by Nordita and or maybe other institutions as well. They have dessert and stuff like that, and then they discuss. So maybe, I don't know, wider topics, but at the same time, I feel like if it's too wide, then you don't bring people in. I understand the struggle.
Yeah, maybe we can have another discussion
Yes,
offline,
yes.
and so we can improve. Yeah. All right. Thank you very much. It was very great to have you. Thanks to everyone else. So I'll see you in 2 weeks. All right. Bye, everyone.
Bye.
Bye-bye.
Thank you.
Bye bye.